Welcome to Breadboarding. This is video 43 part 3 where we're adding an IDE hard drive to the Breadboard 8088 PC, and we should hopefully be then able to boot MS-DOS 3.3 off the hard disk. Now in the previous two videos we've covered the design and background to the IDE disk controller, and in this video we're going to be looking at building the IDE BIOS extensions, adding that to the BIOS EEPROM. Then what we'll look at doing is installing MS-DOS to the hard drive and booting off the hard disk. So in the previous video we had built the IDE controller card down the bottom here. So if you see the highlighted here, we previously had the real-time clock and an I/O decoder here, and what we did is we added another PLD here to handle the control logic. We've got a bidirectional buffer and the 74LS 646 chip, which replaces the two latches from the original XT-IDE design, and then we've got our 40-pin IDE connector over here, which is going to be plugged into a modern SATA drive with a SATA to IDE converter on it. So this is based on the XT-IDE Rev 4 project. We have replaced two of the latches, as I said, with this 646 chip, and we're also using a programmable logic device to replace all of the control logic. We're going to configure it for the Rev 1 compatibility at the moment, so this is theoretically slightly slower. And what we're going to need to do first of all is to configure the XT-IDE BIOS, and we're going to build a tiny mode version of this. So this is just 4K's worth of code, and we're going to configure it with Rev 1 compatibility and the default I/O port of 300. Now you just need to be aware that that 300 port can also be the default for certain other cards like network cards and sound cards and things like that. Then we're going to shuffle the current BIOS up by 4K. So we're going to start it at F9000, not F8000, and that first 4K we're going to put in the tiny mode XT-IDE BIOS, and then we're going to be using our 2.5-inch portable SATA drive with an IDE interface adapter. So let's have a look at the XT-IDE BIOS. The instructions here are up on the XT-IDE BIOS site there. So there's a lot of information on here, but if we want to know how to build it, just need to go into the build instructions here. So we need to check out the code using Subversion SVN. Tortoise SVN makes it easy to do from Windows Explorer, and we also need make NASM as well. So just check to see that our command prompt has actually got those. So if we do make minus version, yep, and NASM minus version, so we have those installed. I've already checked out the code. Once you've installed Tortoise SVN, you can check out fairly easily using the URL that's in the slide there. And if we just check there's any updates, so you can see here we've got our up-to-date source there, and there's a number of folders underneath here which we're going to be looking at in a second. So first thing we need to do, we've checked that we've got NASM and make installed. We're going to first of all go into the universal BIOS make all. Now this makes quite a number of different versions of it of varying sizes, but the one we're going to be interested in is the IDE Tiny. And then what we're going to need to do is to configure this. Now there's another folder here for the XT-IDE Universal BIOS Configurator, and what we're going to do is build that as well. But that is a 16-bit application which won't run under modern Windows, so we need to copy those files over into a DOSBox environment where we can then run the configurator, and this will actually modify some of the code in the binary file there, and will also update the checksum. So this will then allow us to use this file as part of the BIOS EEPROM. So let's build the XT-IDE BIOS. Just check what folder we're in. We want to go into this folder, then we need to type make all. So this is building the various versions. Then we also now need to copy the IDE Tiny into our DOSBox environment. Go to Universal BIOS, build. You can see here these are the various builds we've got. You can see there's different sizes here, but the tiny one is the one which is 4 kilobytes. So this is the one we want, and we're just going to copy that into our DOS folder, which is where I copy the files for the DOSBox environment. Okay, so we've got the tiny there. Now we need to change directory into the configurator v2. Okay, so we just need to type make release here. Do get that message, doesn't seem to matter too much. Maybe there's some extra compression utility I haven't got installed there, but it doesn't seem to make any difference. We just need to copy the XT-IDE configuration.com over into DOSBox. So if we look at build, we've got our XT-IDE config. We'll just copy that into DOS. Okay, so we've got the files there in DOS. So I've got a DOSBox session already running here. So I'll just share the DOSBox screen so it's a bit easier to see. So we need to mount that folder first of all as a C drive. So if we now go to the C drive, we can now hopefully see those files. And now we can run the XTI config.com. Okay, so the first thing we need to do is to load the BIOS from the file. So the XT-IDE tiny.bin there, and we can see at the moment it's 4003 bytes. So it's successfully loaded. Now what we need to do is to configure the XT-IDE universal BIOS. So you go into the primary controller. So you can see here that the master drive, we'll just leave these as defaults, but it is possible for us to change some of the disk parameters there. We haven't got a slave drive at the moment. You can see at the moment it's configured for XT-IDE Rev 1, so this is the sort of low speed mode. The Rev 2 swaps some of the address lines around and allows the PC to use 16-bit I/O reads and writes, which are a little bit faster than the 8-bit versions. But we'll keep that with the Rev 1 for the moment. And you can see that the base address is 300 hex and then the control block is 308. So this will be the CS1 FX and the CS3 FX chip select signals that we'll see on some of the diagrams. We don't need to have multiple controllers, so that's fine, and we only have one IDE controller, and we just need to go into the boot settings as well. So we may as well set this to monochrome since we have a monochrome display adapter. Number of floppy drives we'll set to 1, and we won't bother with removing other hard drives. Okay, so we've now configured it. Now what the XT-IDE card does allow you to do, if you have a flashable EEPROM on the card, then you can actually write this configuration directly into the card itself. But because we're actually incorporating the BIOS in the main BIOS EEPROM itself, then we're not going to use this. So what we do now is to save the BIOS back to the original file. Okay, so we successfully saved our IDE BIOS, and if we actually go back and have a look at the file system, we can see that our IDE tiny.bin has been updated there, and if we go in and have a look at the properties, we can see that in fact now it's 4096 bytes, so it has actually been updated, and there will be a checksum has been updated there as well. So what we will need to do is to add this to our EEPROM at the first 4K block, and we also need to modify the BIOS so it actually starts scanning for extension ROMs actually in that first 4K block of the EEPROM as well. So we've done these steps, we've got our IDE tiny.bin, so the next thing we need to do is to look at some of the other fixes and updates that I've done. So the first fix was a small fix to the monochrome display adapter video controller PLD to adjust some of the timing. And if I just show you what this looked like. So this is a screenshot from the BIOS when it powers up, and you can see that on the right hand side over here that some of the characters at the next line are sort of bleeding into the last pixel there. Now when I ran this with a test pattern with numeric numbers, all 0, 1 all the way down to 25 or 24 down the left and right hand side, then those characters didn't actually exhibit this problem because they weren't using the leftmost pixel. But when you see here, you can see over here that these characters here tend to indicate where we've got M's and W's over here in particular. There's the odd sort of little bits of characters for R's and S's and things, but the M's and W's seem to be the things that show this the most, and you can sort of see that there's a corresponding M there on the previous line. The test patterns that we used for developing the card didn't really show the issue, and the M's and W's are the main one, and there's change timing in MDA clock V3, so it's a fairly minor change you needed to make, but it just made the aesthetics of the display a little bit kinder on the eye. So this is comparing the version 2 with the version 3, and we can see here that we've got the change in timing. We've effectively moved one of the clocks for the attribute and shift register latch. We actually moved it back by 1 clock cycle. So the changes that we've got over here basically have changed the rules for this attribute shift register latch just so that it appears 1 dot clock cycle later, and that's enough to actually fix the issue. As we'll see when we go into the screen sharing, you'll see that we no longer have those stray pixels on the right hand side of the screen. I also had a problem when I was first testing this out, that the StarTech SATA to IDE converter that I had, which I had actually used with the previous project, so the Nanocomp 6809 project, I had a parallel ATA to SATA converter that I got off of Amazon, which was, I think, the cheaper option, but that I struggled to get working on the Nanocomp project. Ironically, the StarTech version, which was working with the Nanocomp 6809, I had problems getting the status off of the IDE hard drive for that one, and I swapped it out with this other one, this no-name brand one, and it actually worked. So this is the StarTech one that I showed in some of the pictures and the earlier videos, and what I have done is just swapped it out with this one. It's just off Amazon, and no particular brand name, and that one similar. It's a very similar thing, just plugs in there. But this one actually worked, so I spent probably a couple of days trying to get to the bottom of why it wasn't working, and then I thought I'll just swap them over, and needless to say, it worked. Also, the IDE PLD configuration, despite the best efforts, needed a few tweaks and things to adjust some of the timing and to change some of the clock signals. So this is on the left hand side, we have the revised version. The right hand side was the version I showed in the previous video. So now the clock signals for the clock BA and clock AB, I've now actually inverted these, so I've made these sort of active low. The reason for that is that we actually want the point where these clock the data to be the rising edge as it goes from low to high, and because of the way how the rules were, we really needed to make sure that this was inverted to make that work. And then down the bottom here, just need to tweak some of these rules and things to make sure that the output enables for the lower and upper bytes and the 2 clocks and things were adjusted. So those have been tweaked to work now, and that PLD has been updated and reprogrammed. And I've also made a few tweaks. Now, I don't know how many of these tweaks were actually necessary, but in trying to get the StarTech parallel ATA to SATA converter to work, I did go over all of the various circuit diagrams I've got of working IDE controllers, and actually went through updating the diagrams and tried various things. So now the main change is really the diagnostics line here, which was disconnected. I've just put a 10k pull-up resistor there just so we can see if there's any diagnostic information. As it turns out, I don't think when you're going through the converter the diagnostic information doesn't come out from the drive, but it was one of the things I did there. There's also a pull-up on the active output. Now that's normally used just to drive the activity LED, but it can also be used to detect status information after resets. And then the DMA acknowledge is just tied to 5 volts. That's like the XT-IDE, and these other 2 ones are pulled down to ground. So these were some of the things I did. So the minor changes to the diagram, but it seems to be working with this current configuration. How many of these things were necessary, I'm not entirely sure at this point in time, but the main thing, it now works. And finally, the XI8088 BIOS looks for extension ROMs, but by default it doesn't actually look in the top 32k. So I needed to modify the BIOS to stop scanning at F9000, which is like the first, after the first 4K block of the EEPROM. Right, it was previously doing F8000, and also now the BIOS has to be configured to start at F9000. So let's just have a look at the changes necessary to configure the BIOS. So this is comparing the BIOS source code, the one where I've done the programmed I/O versus the default with the modifications that I'd made for earlier versions. So you can see here that the scan for the extension ROMs has been, the top address has actually been changed from F800 to F900. So this now extends our BIOS region where it looks for extension ROMs such as our IDE BIOS up to the just below the F9000. And there's a few. We had some of the booting from hard disk was disabled to save a bit of time when doing tests on the previous version I had, so now I had to re-enable the hard disk drive booting, which was commented out previously. So those are the changes in that one. Then configuration, we just need to make sure that at the moment it's starting at 800, and we need to now make it start at 900. So we're just going to copy these details over. So this is defining the start address at 900. So just going to save that. And there are a few other changes we need to make to some of the files where there were specific locations hard coded where it would pad the code out to make sure that the entry points were compatible with legacy BIOSes. I had to remove some of those just to make all the code fit neatly. So those changes necessary. So we just need to go in and make the BIOS. So that's actually built us a new BIOS. Now if we have a look at the binary this has produced, rather than being 32K, we should now find that it's 28K. So this is the binary, and we can in fact say, yes, this is now 28K. So what we need to do now is just to program our BIOS EEPROM. We need to put the IDE tiny bin at the first 4K, and then we need to load this from 1000 onwards. Just start up XT-IDE, which is our programmer. Just need to change this to be the 32K EEPROM. So I said every time, it's always a good idea to read the chip first before you program it. Then at least if you have put it in the wrong way around, it will tell you before it tries to write to it, which I have blown up a few PLDs by putting them in the wrong way around. Okay, so in order to load this, we just need to be careful way how we load this. So the first thing we need to do is, when we load in the tiny IDE, just need to go to DOS, and we need to choose the IDE tiny.bin. So this is the one that we've actually run the configurator on it. Now this is going to start at the base address, and we can clear the buffer with default for this one. So what we should see is the first 1000 here, or 4K in hexadecimal. We should see that when we get to the end there, then from 1000 onwards it's FFF. And now we need to load in our main BIOS itself. Now when we do this, we have to do a couple of things. We need to put the start address in the buffer at being 100. We need to disable the clearing of the buffer, otherwise it will set it all to FF. And we now need to find our modified BIOS. So just check the size. So this is our 28K BIOS. We're not clearing the buffer. We're loading it from 1000. So we can now see that at 1000 we've got our PC88 BIOS, and we should find all the way down the bottom that we've got the jump here. So EA C00F. So this is F000 C000. So that is actually the starting address for the nanocomp monitor, which we boot to by default, so we can actually do a certain amount of maintenance before booting the BIOS. So that looks like we've loaded that in, so we just need to program that now. Okay, so we just need to put that back into the breadboard PC, and we will need to modify the BIOS configuration, so the CMOS configuration, because by default it won't be scanning for extension ROMs. So if we have it by default, we won't be scanning for extension ROMs, so it won't actually find the hard disk because it won't initialize the IDE BIOS. Once we enable the extension ROM scanning, then we should see it picking up the IDE BIOS and also finding the hard disk. Okay, so I've put the ROM in. We're going to need to do some BIOS configuration before this will work, but first of all we need to prepare the IDE hard disk, or the SATA hard disk, that we're going to use for this. So if you take any modern SATA drive which has had modern Windows installed on it, then it will have a GPT boot sector or and partitions. Now these are difficult to remove using MS-DOS utilities, and so as I said in some of the earlier videos, it is possible to wipe the disk with something like a disk eraser utility like dban, and that does take quite a long time. Now DiskPart is actually able to do that as well with the clean all. You just have to be a bit careful that you choose the right disk. So what I've got here is a USB 3 to SATA adapter. So this is a USB 3 to SATA adapter. So I'm just going to plug the drive into this, and then we should be able to erase it using the Windows 11 PC I'm using here. We're just going to start a command prompt. This is an administrator command prompt. We now just move this over so we can see instructions. So disk part, we list disk. So you can see we've got two disks there. The one with GPT, disk 0, is the main drive, 1 terabyte drive that I'm running this off, and disk 1 is the external drive adapter I've got for my 500 gigabyte SATA drive that I want to use for this project. So what I need to do first of all is to select disk 1. Then if I list partition, now in fact this has already got a DOS partition on it. There's about a 15-16 megabyte DOS partition when I was testing this out earlier. Obviously if this is a bigger partition on here, or GPT, then this process would do the same thing. So what we're going to do now is to type clean all. We'll come back once this is finished. Okay, so that finished. Not entirely sure how long it took. It's something like less than 2 hours, but it was more than probably 20 minutes or so. I think clean might take sort of 10, 15, 20 minutes, but it certainly takes a lot less than if we used sort of disk wiping software like dban, which would take 7 or 8 hours at least. So the disk is now cleaned, so we can now eject that and plug it into the breadboard PC and see if we can boot up MS-DOS or floppy disk and see if it sees the hard disk. So we'll just eject the disk. Okay, it's safe to remove. And before we plug the SATA drive in, I'm just going to need to go into the BIOS configuration and get it to scan for the IDE extension ROM. Okay, I'm just going to power on the nanocomp, and we're going to press F1 as it's booting up. So you can see here we've got the F1 to run BIOS, and once the memory test is finished, now if we go into the BIOS and print out the current configuration, see the date and time are pretty accurate. We've got one floppy drive. You can see here that the F0000 to F8 FFF BIOS extension scan is disabled. So we need to turn that on. So we go into E for extension, yes, and then right. Now this is just going to boot MS-DOS 3.30 off the floppy disk. Okay, can see that it's coming up with the date correctly and the time, MS-DOS 330. Right, so we're ready now to plug in the hard disk, and it should now detect the IDE BIOS, and we should now get a second screen which shows it looking for the disks. Now at the moment there's no operating system on the disk, so it shouldn't boot off that. It should then boot off the A drive. Okay, so I've plugged in the disk drive into the adapter, and we're just going to power this on. We've already enabled the extension scanning for the BIOS. So once this has tested the RAM, it should then go and detect the disk drives, but there won't be any operating system, so it will still boot off the A drive. Now I've disabled the second drive scanning, so now hopefully we should not confuse MS-DOS with the number of drive letters. Right, so now we've got our A drive. We'll just have a look at what files we got on there. So once we've booted MS-DOS 330 from floppy disk, we need to go into F-disk. We need to create a primary DOS partition. We're only going to use 2 cylinders. That will make it about 16 megabytes, and that will allow us to use PC-DOS 210 with it. If it's any bigger than that, then the file system won't be known by PC-DOS. PC-DOS 210 used FAT12, whereas I think 3 upwards has FAT16 support. We also need to set the primary partition to be active and then to reboot, and then we'll need to try and format the hard disk, and it should be coming up as a C drive. Let's now go into F-disk, display partition information. There is one fixed disk, which is good. We want to create a DOS partition, create a primary DOS partition. We don't want to make all of the space available. Now this will take a little while after pressing escape. There we go. So it's saying the maximum space available per partition is 4 cylinders, so that would make it about 32 megabytes, which I think is the maximum partition size that MS-DOS 3 upwards can deal with until we got to larger disk sizes. But we're just going to make it 2 cylinders for the moment. So the partition has now been created. Now if we change the active partition, make our partition 1 active, so that's active now. If we now just display the partition information again, so we should now have an active partition which we can then format, assuming that MS-DOS detects it as the C drive. So now we just need to reboot. Okay, so after quite a bit of investigation, what I was able to determine is that MS-DOS 330 doesn't seem to be very happy formatting the C drive. The drives seem to get mixed up. When I booted the floppy disk drive off of MS-DOS 5, MS-DOS 622, then it actually picked up the C drive exactly as it should have been, as expected. So what I ended up doing is I've actually put the drive in another PC. So what I've done is I've checked that, and in fact it did actually have the correct MS-DOS 3.3 boot sector in there already, but I was able to format it /S. So now what I've done is I've put the drive back in. So we do actually have a very basic operating system, MS-DOS 3.3.0. So we're going to boot it back up again now and see. I've taken the floppy disk out, and we'll see whether or not we can actually get it to boot MS-DOS 3.3.0. I suspect it might still come up as the D drive rather than the C drive, although if we do the same thing with later versions of MS-DOS, it appears to come up with the C drive correctly. So let's now have a look at the screen share, and we'll power on the Breadboard PC. So it should go onto the second screen for the IDE BIOS. It's trying to boot off the A drive, but it doesn't find a floppy disk in there after it's retried, I think 2 or 3 times. So now it's actually trying to boot off the D drive, not the C drive, but is actually finding an operating system there. So looks like it is working now. I'm not entirely sure why it's picking up as the D drive. Certainly the fact that MS-DOS 5 and MS-DOS 6 don't get confused indicates it's probably a DOS related thing, or interaction of DOS and the XT-IDE BIOS. So what I'm going to do now is to copy some of the files from the floppy disk over onto there, just so that now I've got all the things that I had on the floppy disk drive and Norton utilities and everything. So we're just going to copy those over, and then once we finish that, we should be in a position to do a little bit more exploring of the hard disk. Okay, so that's copied the files over. I'm just going to go onto the D drive and check that they're okay, because when I've tested this out in the past, sometimes the larger files didn't get copied over. So if you just try Norton Utilities, that seems to be working okay. So choose the root directory, display edit the item, and we can see there we've got our io.sys, msdos.sys, command.com, Norton Utilities, and our other folders and things. And we can also see that io.sys and ms.sys are also read-only system hidden files, so we wouldn't be able to see those with this version of DOS under normal circumstances. So I'll just go and check to see if the Zork works. Yep, that seems to be working, so we can start it up anyway. And then finally, we'll just have a look at the Norton editor. So that's the Norton editor. It's certainly a lot easier to use than the Edlin editor that comes bundled with MS-DOS. So that all seems to be working okay now. I've got two other utilities on here. So if you go into Tools, so CT is a display test, so CGA and MDA Hercules card test. So if we do CT, then the mode, now the only mode that the MDA card knows is mode 7, which is a text mode. So this just shows the ROM character set, which looks like it's all correct, and then just shows all various attributes. So you can see there that we've got the normal bright underlined and all the reverse and blinking. So that's all working okay. Now there is another program in here, IDE Info. It doesn't work brilliantly on this version, but does come up with some information. It does say that this is currently detected as one hard drive and it's coming up as one hard drive 1, so it doesn't seem to give us a massive amount of useful information, but does seem to indicate that under this version of MS-DOS that it's identifying as drive 1 rather than drive 0, so that probably explains why we've got the D drive. The fact that when we boot up in later versions of MS-DOS this is actually drive C indicates there's some sort of issue going on somewhere, so I'm not going to worry too much about that. Looks like we've got this now working, and what I'm going to do is to look at some more software to put onto the hard drive so we can actually dig into MS-DOS 3.3.0 a little bit more detail. So I'm just going to go into Norton Utilities again just to have a quick look at the information. So just going to choose the boot sector, that's 00. And we can see here again, so we've got the MS-DOS 3.3 boot sector. As long as I'm able to format it on another PC, then it seemed to have been okay. This was the actual F-disk boot sector that was created actually on the Breadboard PC. It's just the formatting seems to have got itself a bit confused between the C and the D drive. So what I'm going to do is to break the video now. And coming up, what I'm going to be doing in the background is building a CGA color video controller. So this is going to be based on some of the work we've already done on the monochrome display adapter video controller here, but it's going to be adding graphics and things like that. Now this is going to take a little while, so in the meantime what I'll probably also do, I'll do a couple of videos about exploring MS-DOS in a bit more. So at the moment we haven't got any configuration files, we've not really looked at any of the utilities or any of the MS-DOS sort of capabilities between the different versions. So what I'll probably do is over the next couple of weeks a few videos around MS-DOS whilst I'm actually working on the CGA video controller in the background. So thanks for watching. If you don't want to miss out on future videos, please hit subscribe, and if you can hit like as well, it just helps to make the videos available to more people. Thanks for watching.